Welcome back to the another class of fundamentals of particle and fluid solid processing. We will continue with our concept on the fluid flow through granular and packed bed of particles. In the last class we solved this problem which we will quickly go through once again for the sake of continuity, and we will solve couple of more problems related to the idea that we have seen theoretically. So, the problem mentions that this is there is a water that flows through 3.6 kg of glass particles of density 2590 kg per meter cube, forming a packed bed of depth 0.475 meter and diameter 0.0757 meter. The variation in frictional pressure drop across the bed with water flow rate in the range of 200 to 1200 cc per minute, that is given in the table. We have to calculate, or we have to show at first that this flow behavior is laminar. We have to estimate the mean surface volume diameter of these particles, and we have to calculate the relevant Reynolds number. So, the problem is given this, the data that are given that water flow rate is mentioned and pressure drop is given. So, for known water flow rate, pressure drop is mentioned, but water flow rate is mentioned in cc per minute. Pressure drop is given in millimeter mercury. So, corresponding flow rate as we increase, we have seen the pressure drop also increases. Now, the first point is that we have to establish that flow behavior is laminar. So, for that, what is that the thing that we did? At first, we converted these units to a consistent unit, that cc per minute to meter per second, that is in terms of a superficial velocity, and the pressure drop from millimeter mercury to the Pascal. So, the reason that we did, because the Argand equation, the first part of the Argand equation, since it has been mentioned that demonstrate the flow is laminar. So, assuming that it is laminar, so the first part of the Argand equation is given here, and we can see that the pressure drop, okay, is linearly varying with the superficial velocity. So, that from the water flow rate, which is Q, okay, we know the cross sectional area because the diameter is given here. So, we can calculate Q by A, which is the superficial velocity here, and we know the pressure drop. So, if we plot that, and if it is linear with the slope of this parameter, then undoubtedly this flow is laminar, and this is what we have done here, that over this fluid velocity, the superficial velocity capital U versus del P is plotted here, okay, and we see these points can be fitted with a straight line, which means it establishes that the variation of pressure drop with superficial velocity is linear, so the region is laminar. So, this is established, and as we have seen that if this is laminar, then this del P versus U, this plot will give you a slope of straight line, this value, this is y is equals to mx plot, where m is this value, okay. So, this the slope of this graph that we get is, if you do this numerically, again this graph is not to the scale. If you draw that, if you have it with the accuracy, you would find that the slope is this value, which is nothing but this parameter that we have shown earlier, okay. The second question was determine the surface volume mean diameter, okay. Now, in this expression, this is what has been asked. In this question directly there is no mention of voidage. What is the voidage? Okay. So, In this expression, mu is given, height of the bed is known. This epsilon was not directly mentioned, but it is mentioned in terms of the mass of bed. Now, mass of the bed is nothing but the volume of the solid particles multiplied by its density. The volume of the solid particle is the cross sectional area in which the solid is retained or the contained. Now, since this is a stack of particles, let us say this is the particle stack. So, there are voidages inside through which flow happens. Okay. So, if the voidage is epsilon, then 1 minus epsilon is what the solid fractions are, multiplied by the cross section is where the solids are retained in the cross sectional area, multiplied by the H is basically is your volume. This multiplied by its density gives the mass. By equating that, mass of the bed is known. Here it is mentioned as 3.6 kg, which gives, and all these values are given in the problem statement. So, it results this epsilon as 0.3497. Once we have that, we replace now here this epsilon in this expression. All values are known. So, epsilon known, H known, mu is known. So, we get what is xv, and that xv comes out to be 792 micron. This is our surface volume mean diameter. We have to calculate relevant Reynolds number. Relevant Reynolds number definition for the Argand equation is this one, where x is the diameter or the equivalent diameter, superficial velocity. This is your density of the fluid, mu viscosity of the fluid, 1 minus epsilon is the 1 minus voidage. If we now replace all these values, we get Reynolds number as 5.4. Now, this u here is a range that is given. If we take the maximum one, because that is the maximum Reynolds number that can be possible for a fixed property of liquid and the solid. If we take that, we get the maximum Reynolds number for the range of the study is 5.4. So, definitely the other results are well within the laminar region. Okay. So, this was the first problem that we solved. Okay. Now, we move on to the next problem. The problem says that a packed bed of solid particles of density 2500 kg per meter cube occupies a depth of 1 meter in a vessel that has a cross sectional area of 0.04 meter square. The mass of solids in the bed is 50 kg and the surface volume mean diameter of the particles is 1 millimeter. The density of the liquid is 800 kg per meter cube and viscosity 0.002 Pascal second, flows upward through the bed which is restrained at its upper surface. So, we have to calculate what is the voidage or the volume fraction occupied by the voids of the bed. And the second part is that calculate pressure drop across the bed when the volumetric flow rate of liquid is 1.44 meter cube per hour. So, the problem is we have a packed bed where the solid particles are there of known density, rho p is given. Okay. So, rho p is mentioned here, vessel cross sectional area is given. Okay. The mass of solid of the bed, if the bed height is this one, okay, the mass of the solid, that is m, is mentioned, xsv is given. Okay. The liquid that goes upward that rho f is also mentioned here and mu of the liquid is given. So, we have to calculate what is the voidage, that is the epsilon at first, and the pressure drop across the bed when this flow rate is 1.44 meter cube per hour. This is the overall problem statement. So, how do we solve this? Do we know the flow region? Because if that is clear, then we can either use Koizumi-Kármán or Bark-Plummer, but here that is not clear, because eventually this voidage, that information is unknown, because Reynolds number calculation involves this voidage. So, without that calculation, let us use Argand equation here, because that encompasses the whole region, okay, for the pressure drop calculation. But before that, the voidage calculation is simple again, like we did, because we have to equate this mass of the solid particles with the void, the fractions multiplied by the volume, the bed volume multiplied by the its density. If we do that, we can have the xv as well, the epsilon or the bed voidage here. So, which is again the mass of the bed is the cross sectional area of the solid multiplied by the height, which gives the volume multiplied by the rho of the particle. Okay. So, then if we equate that with the known quantity, we can have an expression then that gives us the value of epsilon, because here then other parameters are known. Mass of the bed, that is given as 50 kg, okay, rho p, cross sectional area, and the height. So, this depth is 1, cross sectional area is given. So, all the parameters are known. So, we can find what is the bed voidage. This is the first part is answered. Then the second part, it says when the liquid flow rate is 1.44 meter cube per hour, what is the pressure drop across the bed? Okay. So, for that we need the superficial velocity, which is again simple to derive, which is the volumetric flow rate divided by the cross sectional area through which flow is happening. In this case, the value comes out to be 0.01 meter per second, the superficial velocity. This is what we require in the Argand equation. Now, in the Argand equation, we have all known parameter. xv is mentioned, mu is already we have taken into account, u we have calculated, epsilon is what we have calculated. So, in all the cases, similarly this here rho if is mentioned here in this problem. So, the right hand side, all the parameters are basically known to us now. With that, then we can calculate this minus del p by h value. So, this is again the summary, that we have mu del rho f, which is the fluid density, we have the particle size, we have the depth of the bed. So, the inertia term and the viscous term and the inertia term. And we have from the value of u, we can find out that pressure drop comes out to be 6560 Pascal. This is the answer, but then again let's check that what is the Reynolds number based on the U that we have now calculated. If we calculate that, we see that this Reynolds number for this problem with Q of 1.44 meter cube per second, that is meter cube per hour, we have the Reynolds number as 8, which means it is in the laminar region, and in the laminar region we could have applied Koenig-Karman equation. If we apply that, we get 7200 Pascal. Del P by J is the pressure gradient, the pressure drop per unit depth or per unit height. Now you can ask that there are two different answers, that what if after this stage, once we know U, we could have calculated Reynolds number, and then instead of using Argand equation we could have used Koenig-Karman equation or the Karman-Kozen equation. That is also a valid approach. Okay, but the reason for showing these two, that these two yields in two different numerical numbers, or in fact after calculating this Reynolds number, particle Reynolds number, one could have used only the first part of the Argand equation. That means only this part, only the viscous part, neglecting this inertia part, because in laminar flow we have mentioned repeatedly that only the inertia term that makes the most of the contribution. And in fact, if you calculate this part only, you will see that this part numerically equals to 6500 Pascal. So in fact most of the contribution, all of the contribution comes from only the viscous part, because the flow is laminar, which means now we have three numerical the results. One one can come up with 6500, the other person can come up with 6560 Pascal, the third one can come up with this value. All the results are fine. Okay. Now which one you should take during the design? It's quite obvious that if you take the higher value, you can always have the margin of safety during the design. This is almost 1.2 times of this initial value, that 1.1 times. Okay. So if it comes to the design purpose, we can use the highest value, highest pressure drop expectations, because then if it is lower, our designer safe. But if you start the design with 6500 and somehow because these results are varying because of this constant, this 180, 150, this constant, and these are the empirically fitted constant for the different shape or the size of the particle and of different surface property. Okay. So the best way to have by several experiments, when that is not possible or not feasible, we use these combinations and find out which one is the highest, and we take that into the design consideration to be with the margin of safety. So I hope this problem is clear to you. Very simple problem, but the point is how do we calculate the epsilon and how we justify our answers, that is one of the main issue. Okay. So then we move on to the other problem. This problem says that a gas absorption tower of diameter 2 meter contains ceramic Raschig rings, which is a cylindrical kind of hollow cylindrical kind of a structure that is very popular in the industrial applications, that is randomly packed, okay, to a height of 5 meter. Air containing a small portion of SO2 passes upward through the absorption tower at a flow rate of 6 meter cube per second. The viscosity and density of the gas phase are given. The details of the packing, because this is a typical packing, this is not kind of a regular structure. I mean, it's not like we have a systematic calculations for that. So this Raschig ring, the properties are given like the surface area per unit volume of the bed, that is mentioned here, SV value. So the surface area of the particle per unit volume of the bed, remember, SB stands for the surface area per unit volume of the bed, and the voidage value is 0.71. The purpose of using this Raschig rings is to create the voidage area more and more. This kind of structure increases the void spaces, so that our phase when the interfaces becomes larger and larger, the contact area increases when a fluid flows through those particles. And if that happens, in several cases we need that maximum surface area available for the particles to the reaction to happen, absorption to happen, and such things. So here we have to calculate the diameter of a sphere with the same surface volume ratio as of the Raschig rings. This is the first part. So we have to calculate the diameter of a sphere having the same x is V of the Raschig ring. We have to calculate the frictional pressure drop across the packings in the tower, del P by H minus del P by H. We have to discuss how pressure drop will vary if the flow rate of the gas changes within the 10% of this range. That is the flow rate that is mentioned here. Okay, and we have to also discuss how the pressure drop across the packing would vary with gas pressure and temperature. We have pressure and temperature. What are the things it changes, so that the things that this del P by H, how it varies. Okay. So this is again the similar kind of a problem that we have solved, at least the first two parts. We have the information of SB, which is the surface area of particles per unit volume of the bed. Let us convert that to the surface area of the particles per unit volume of the particle. Okay. So that is the surface area per unit volume of the Raschig rings. This multiplied by 1 minus epsilon is that value, the SB that is given. This we have discussed earlier, which means the SB that is here is 655.2 meter square per meter cube. Okay. So now if SV is the diameter of the sphere, okay, then the same surface volume ratio as the ring that we have that we are looking for the sphere, which we can calculate from this expression, that the surface area of a sphere having the diameter x SV, and this is the volume of that spherical object. By equating that with this value, we can find out what is XSV, or the diameter of the sphere with the same surface volume ratio as of the Raschig ring. Okay. So basically in the first part we had to convert that surface area per unit volume of the particle of the bed to the surface area per unit volume of the particle. okay, and then we can have this XSV value, and then we move to calculation of superficial velocity, which is 1.91. How we get that? We divide the volumetric flow rate with the cross sectional area, we get the superficial velocity, and now other informations are mentioned, that is mu, rho f, XSV we have calculated, and height is 5 meter. We use it in the Argand equation and we get that the pressure drop, the overall pressure drop is 3460.4 Pascal. This stage shows that all the numerics that are replaced here. It is also explicitly shown here that the contribution of the first part, the contribution of the second part. What did you get? Is that the overall pressure drop has most of the contribution from the inertia part of the Argand equation, almost 98%. Okay, so the turbulent component contributes 98% of the total, which means that flow is happening in the turbulent region. Okay, the question was how, if we change the flow rate within the 10%, how the pressure drop will vary. The answer is, since it is the turbulent part that is contributing more and more in this expression, or more and more in this result, and you can see it is 98%. So that means even if you change plus minus 10%, it will still be in the turbulent region, and if that happens, then del P varies with the u square value. Okay, superficial velocity square. Q is proportional to the value u. As you increase the superficial velocity, flow rate increases. So it would increase in that proportion. The del P would increase in the same proportion of the superficial velocity if you change the flow rate. The question is whether there will be any influence of pressure and temperature of the gaseous phase. Okay. Now the pressure increase influences only the gas density. Okay. So if the gas density changes, which is the fluid density changes, that means what will happen? Del P and rho f, what is the relation? If rho f increases, del P will increase. If rho f decreases, rho P this del P will decrease. So it's proportionate relation, linearly proportional in this case. The gas density is directly proportional to the absolute gas pressure. Okay, the ideal gas behavior, if we assume the gas will behave as ideally. So this is the assumption we make, that okay, this air that is flowing will behave as an ideal gas, and then we have this relation that it will be changing proportionately. Now coming to the temperature part, the gas viscosity basically has no influence in this component. Viscous effect is dominated here if it is laminar case. Okay. So the point is that gas temperature will influence only the gas density. Now assuming again ideal gas behavior, we can see this is the relation between the density and the temperature for ideal case, ideal gas, where T is the absolute temperature. Okay. So what will happen? If you increase the temperature, the gas density will decrease, and so the pressure drop. So the temperature will have similar effect, okay, as of the density, I mean inversely proportional to the density. So I hope this is clear, that this small concept, that what would be the effect of temperature and pressure if there is a fluid phase that is of gas and that contains different temperature and pressure, what would be the variation and how it affects or how it influences the Argand equation or the Koenig-Arman equations or the Bloch-Plummer equations. So and with this note, I will stop here today, and we'll be coming up with the more problems in the next class. Okay, thank you for your attention.